Welcome to the Crazy Hat Chemist. So another video here on acids, bases, and titrations. Hey, before you get started on this video, you need to review video 21A, B, C, and D before you start with this last one with part E. Hey, notice, look at what I'm wearing here. I got the Crazy Hat Chemistry t-shirt. Oh yeah, look at that, baby. All right, so let's get going. Bam! So today, titration example number 3, we're going to do a past the equivalence point calculation. Okay? Past the equivalence point calculation. The first recognition here is that with the addition of 52 milliliters of sodium hydroxide, one has passed the equivalence point. The equivalence point is 50 milliliters. We already made that calculation in part C with the equivalence point endpoint. Okay? To determine the pH past the equivalence point, one must understand that at this point in the titration, one is past any buffering capacity, and the pH is completely dictated by the excess strong. And that is, in this particular case, it is the sodium hydroxide. So we need to calculate the amount of hydroxide ions in concentration, that is moles per liter, that are in excess. That is our process that we're going to do here. So we're going to calculate the moles of acid that were here inside the flask. Same calculation that we've done multiple times throughout this entire problem. That's 50 mils times the unit conversion to convert from milliliters to liters times the molarity of the acetic acid. That is a 0.1 molar. Canceling out the milliliters, canceling out the liters, I have 0.00500 moles of acetic acid. Okay? Now, we're going to calculate the moles of base that is added. Now, we are adding 52 milliliters of sodium hydroxide, and that is base. So we got 52 milliliters using the unit conversion from milliliters to liters, and then the molarity of the sodium hydroxide at 0.100 molar. That will give me 0.0052 moles of sodium hydroxide that is added. Now remember, the 50 mils of sodium hydroxide is at the equivalence point, so we are most certainly past the equivalence point. And in order for you to really understand that, you needed to have done the 3 or 4 prior calculations to this one. Okay, we're going to subtract these values here. Now this will give me 0.00020 moles of sodium hydroxide. This is the amount of base that is in excess, that is past the equivalence point. So what is the concentration of this sodium hydroxide past the equivalence point? We need to get the total volume. Okay, we have the volume of the acid, we have the volume of the base that's added. So we have the volume of the acid, that's the 50.0 milliliters. We have the volume of the base that's added, that's the 52.0 milliliters. That equals 102.0 milliliters total volume. Okay? We know that sodium hydroxide is a strong base, therefore it dissociates 100%. And the sodium ion is a conjugate to a strong, so therefore the sodium ion does not contribute to the pH. You need to watch some previous videos on that. Okay, so we're going to calculate the concentration of the hydroxide ion that is in excess. So we're at the concentration of the hydroxide ion. So what's the amount of hydroxide ion that is in excess? That is past the equivalence point. That is 0.00020 moles of sodium hydroxide or hydroxide ion in 102 milliliters. I've converted that into liters. This will give me a value for the concentration of the hydroxide as 2.0 times 10 to the 3 molar. Okay, so now I'm going to calculate the pOH. The pOH is the negative log of that concentration, and that will give me a pOH of 2.70, 2 decimal places. Okay, pH plus the pOH is equal to 14.00. That's one of our definitions. We're going to plug in the pOH into this, then subtract 2.70 from both sides, and we're going to get this magic number of a pH of 11.30. So the pH past the equivalence point by adding 2 more milliliters of sodium hydroxide past the equivalence point because we're at 52 mils, so it's 2 more mils past the equivalence point, we have a pH of 11.30. That means that that pH has gone up from past that 8 at the equivalence point, okay, to shooting up at 11.30, because we don't have any more buffering capacity at all whatsoever of the conjugate pairs. The conjugate pairs are all gone, and we just have excess hydroxide ion. And that's why it's so basic. And that number should make sense on the graph. So I want you to go back to 21A, that video of 21A at the very beginning of this problem here, and look at that one and look at that graph. And that graph just keeps on going up. Okay, I am the Crazy Hat Chemist, and of course, okay, I got a little joke here for you. See, I made this chemist parking only, and I'm holding a bottle of nitric acid there, okay, and that's why I'm wearing my goggles and my lab coat, of course, because all others will be dissolved. If you park in my parking spot, I will take some hydrochloric acid, or maybe nitric acid, or maybe the combination of both to make royal acid. Okay, or regal acid, and then dissolve your automobile if you park in my parking spot. Okay, I am the Crazy Hat Chemist, okay, of course, and I got a Crazy Hat Chemist t-shirt, okay? You gotta donate to my website, get one of these. Got the website right there on the back, okay? If you donate, you can get yourself a sticker for your hydro flask. It's right there. It's super cool. It's what you need, okay? I'm the Crazy Hat Chemist. I'll see you next time for another unit on more cool chemistry stuff. Give me a thumbs up if you like that video. Pass on my videos to all your favorite friends. Pass on my website. Donate to my website so you can get the merchandise. Bye for now.